Hello everyone, my name is Feng Zhang. I'm going to present our work on enabling efficient random access to hierarchically compressed data. This is a joint work of Renmin University of China, Tsinghua University, North Carolina State University, and ICDE. This is the outline of our presentation. First, let's look at the background. Taiduk, text analytics directly on compression, is a technique we proposed in VLDB 2018. Taiduk can perform text analytics directly on compressed data without decompression. Here, I just gave an illustration. Figure A shows the original files. File 0 and file 1 are two files, and WI represents a word. Figure B shows the Taiduk compressed data, which uses rules and words to represent the original data. Figure C shows that the rules can be organized into a deck, so the original data analytics can be traversed into a graph traversal problem. Figure D shows a numerical representation, where we use numbers to represent words and rules. Figure E shows the compressed data in numerical form. This is an example of how to perform word count on Taiduk compressed data. In the first step, Rule 2 transmits its word frequencies of W1 and W2 multiplied by its rule frequency to its parents, Rule 0 and Rule 1. In the second step, Rule 1 transmits its accumulated word frequencies multiplied by its rule frequency to its parent, Rule 0. In the third step, Rule 0 calculates the final results. By leveraging the hierarchical structure of the compression format, Taiduk avoids repeatedly counting text segments that appear many times. Although Taiduk provides good performance, it is not efficiently applicable to all text analytics queries. Specifically, such compression-based analytics techniques do not support random accesses. Text analytics is fundamentally based on two types of operations on text: traversal operations and random accesses. Traversal operations traverse the entire text corpus. Examples include word count, inverted index, sequence count, and so on. Random accesses, on the other hand, require visiting arbitrary locations in a text document. They are no less common than traversal operations. Previous Taiduk only relates to traversal-based operations, but not random accesses. In our daily life, we may need random access operations on data such as news, files, and logs. For example, we may need to search for a certain word or extract a certain piece of data. Based on our analysis, we have summarized 5 common random access operations: search, extract, count, insert, and append. To support these 5 types of random accesses, we'll observe several principles. First, locality. These operations are random accesses to specific locations, which needs the ability to quickly locate the required place. Second, compatibility. We should preserve the compatibility of Taiduk to support previous efficient traversal operations, since Taiduk already supports traversal-based analytics. Third, user transparency. Users should not need to be concerned about the implementation details, but simply use our provided operations. To realize the three properties is not easy. We need to handle several challenges. The first challenge is hierarchical structure of the DAG. In the DAG, one node could have multiple parents and may belong to different files. For example, row 2 belongs to both row 1 and row 0, and even in different files. If we want to count the frequency for W1 in file 0, even if we find out that W1 appears in both row 0 and row 2, we still cannot tell how many times the word appears in file 0 as row 2 belongs to multiple files. The second challenge is unidirectionality. Previous Hadoop can only traverse the DAG from the root, since the DAG is a unidirectional data structure. Even if we can locate an interest node, it is difficult to identify the node's sister nodes. The third challenge is spatial complexities on insert. Because a rule may belong to multiple parents and represents multiple pieces of content, we cannot insert directly into the rule. For instance, suppose that one wants to insert W7 right after the third word in file 0. If we insert it directly into rule 1 after W3, the consequence would be that file 1 now have W7 inserted twice at each of the places where rule 1 appears, as shown in the content of rule 0. The fourth challenge is trade-off between space savings and time cost. To support efficient random access, some indexing data structures may have to be added. If the new data structures incur large space overhead, the advantage of the technique will reduce. This figure illustrates the main challenges and our solution techniques. To address the challenges against efficient random access on hierarchically compressed data, we develop 5 data structures: rule to location, word to rule, root offset, bitmap, and records. These 5 data structures are designed to help address the challenges. To address the first challenge of hierarchical structure of the DAG, word to rule and rule to location build the relation between words and offsets. To address the second challenge of unidirectionality, using the first 3 data structures, rule to location, word to rule, and root offset, we can perform local graph walks rather than traversing the graph from the beginning location for each random access. To address the special challenge on insert, the beads in bitmap are used to identify why the new content is added in each location, and the new content can be stored separately in records. Finally, to save space cost, these data structures are selectively stored. We show an example of the relations of these data structures in this slide. Rule to location and bitmap are separate data structures, which means that each node has these data structures, so they have many instances embedded in each node. The other data structures are single data structures that have only one instance. Word to rule and root to location are for entire deck, and the root offset is only embedded in the root node. The extract operation extracts content directly from a compressed file. The root sequence provides the pointers from children to parents, which enables the random movement from any node in the deck. To extract a piece of content, we can use binary search among offsets to quickly locate the starting unit. Then, after we locate the starting unit, instead of deck traversal, we go through the related rules with the help of the rule sequence data structure until we obtain the required content. The word to rule and rule to location data structures can be used for search and count. The word to rule provides a mapping from words to rules. The rule to location provides a mapping from each rule to the location. We have special optimizations for the proposed data structures. For example, the figure shows the optimization for rule to location, which makes it more compact. We store the newly inserted content into a separate data structure, the record data structure, which contains necessary data for an insertion. For insert operation, it first finds the offset, and then sets the corresponding bitmap and insert the content into the records. Finally, it updates the root offset buffer as the newly inserted content may change the starting offsets of some rules. The append operation also changes data, but it is much simpler than insert, because the new content needs to be appended exactly at the end of a file. We evaluate the efficiency of the proposed support in terms of both space and time savings. For evaluation, we evaluate the 5 operations with 5 datasets on 2 platforms, including a single node and a Spark cluster on Amazon EC2. We compare our method, compress direct, to the state-of-the-art technique, succinct. This figure shows our throughput results on 3 large datasets. On average, the overall throughput of our proposed technique is 3.1 times of succinct throughput in a distributed environment. We measure the space savings using the compression ratio metric, which is defined as the size of the original data divided by the size of the compressed data. The space-saving results are shown in this figure. The compression ratio of the original Taiduk is high. The newly added data structures inflate the space. However, the average compression ratio we observe is 3.9, which is still much more compact than the 1.8 compression ratio of succinct. Here is our conclusion. We provide a set of new techniques that enable efficient random access operations on hierarchically compressed data. Our techniques are compatible with Taiduk, which supports data traversal operations. We remove a major barrier against the practical adoption of direct analytics on compressed data. Thanks. Any questions?